Switching topics now, this video is going to cover correlation and regression. Correlation and regression look for associations. So when we talked about t-test and ANOVA, we were talking about differences between groups or among groups, depending on whether they're talking about t-test or ANOVA. Now we're talking about how things are related to one another. And let me give you a typical example for this. So we use for graduate school, in some cases, the GRE to predict GPA. And the idea here is when you draw the graph, the thing you think is the predictor is always on the x-axis and the outcome is always on the y-axis. And GRE scores can range from low to high, and GPA can range from low to high, and it doesn't matter what the exact values are. It's the idea that we're going to talk about today. So does GRE predict GPA? Are they related? Is there something there? And the research shows that yes, there is. That as GRE goes up, as people get higher GRE scores, they get higher grad school GPAs. And I'm going to put dots on here. And each dot is one person. So we collected some data, and this person got a fairly low GRE score and a fairly low GPA. And this person got a fairly high GRE score and a fairly high GPA. And now each dot is a person. And the people are scattered all over that graph. And I don't know how many dots I'm going to draw, but you get the point that each one of these. And generally, when considering correlation, you put an oval around the dots, and it shows you in general how much variability there is in that relationship between GRE and GPA. And that's what we're talking about when we talk about correlation. So the person I started with, low and low, and the person I second, high and high, but there's also this person who got fairly high on the GRE and low, and we got this person here who got fairly low on the GRE, but got a fairly high GPA. It's an imperfect relationship. There is a relationship. That oval goes up, but it's imperfect. There's error in there. Back to that equation of error. It's what we want to know in the top and what we don't know in the bottom. Now for correlation, and again, if I ruled the world of statistics, I wouldn't abbreviate it with an R, but for some reason, correlation is abbreviated with an R. So the R value is calculated by the relationship you know about in the top and the error in the relationship in the bottom. So it's what you want to know in the top and what you don't know in the bottom. It's actually what's called the covariance in the top and the error in variance in the bottom, but nonetheless, it's still this idea about what you want to know in the top and what you don't know in the bottom. And a correlation coefficient can range from 0 to -1 to +1. Now, there's two parts to a correlation coefficient. There is the sign, which indicates the direction. Now, direction, as one thing goes up, the other thing goes up. As one goes down, the other goes down. They vary in the same direction. That's a positive correlation, and that's what I'm indicating here. There's also the absolute value of the number, which indicates the strength. So a -1 correlation is a perfect negative correlation. A +1 correlation is a perfect positive correlation. 0 means there's no correlation. So actually a -0.8 correlation is stronger, is better than a +0.2 correlation. So that's indicating strength of the relationship. Sign indicates direction. The value indicates strength. The closer it is to 0, the more it's like no relationship. So if we did the relationship between foot size and ignore the, women and men have different measures, but you can have a foot size from 4 to 13, let's say, and we can have GPA. And these dots would be all over. You couldn't do an oval around these. In this case, it would be, hopefully, foot size is not related to GPA. It would be a correlation of approximately 0. There would be no correlation. Now, we could also do number of hours worked at your real job, your day job, and you could do 40 to 60, and GPA, let's say 60 is the high, maybe higher for some of you, and maybe what that relationship would be is, and putting dots again, and the oval would look more like this, and that's a negative correlation. As you work more hours in your day job, in your real job, your GPA goes down. You have to carve out time for your graduate studies. So that's a negative correlation. So you see a positive correlation, the GRE and GPA, and now a 0 correlation and a negative correlation. And we're going to go back to this first one, the relationship, the positive correlation. Now, you could draw a line of best fit through the middle. That's your estimate. And it's generally about the end to end in that oval. And you can see that the error in the y-axis, okay, goes from about there to there. It means this isn't a very good correlation. And that's the fact with GRE, is that the GRE is correlated with GPA at about, depending on the study that you look at, the R is approximately 0.3 to 0.4 positive. So it is predictive. It is statistically significant. There's plenty of research showing that. Now, let's talk about correlation. Statistically significant. It is either statistically significant or not with the effect size measure. And you might remember when I talked about effect size measure, it's simply the R squared. And the R squared would be approximately 0.3 squared, which would be positive 0.09 to 0.4 squared to about 0.16. And again, this is real data. This is what the research shows. I've read quite a few of these studies. Now, the beautiful thing about correlation coefficient is it's the predictive validity. The R squared indicates the percent of your outcome that's predicted by the predictor. So in this case, what percent of GPA is predicted by GRE? Well, it's 9 to 16%. And again, that's really good in the social sciences. That's what we like. We like predictions like that. Wow, 9%. But that means that 91% to 16% is predicted. That means 84% is not predicted. Our error is pretty high. So GRE is a good predictor for the social sciences, but it's missing a lot of stuff, as you might suspect. It's missing motivation, and it's missing effort, and it's missing past experience, and it's missing how well you work in teams, and on and on and on. So the sign is the direction. Positive correlation, negative correlation, 0 correlation, and the strength has to do with how big this oval is. A perfect correlation is everything's on the line. An imperfect correlation, this one, there's a huge oval, and the bigger that oval, the worse the correlation coefficient. Now, we're going to go to one more step here, and we are going to talk about regression. Regression is one step beyond correlation coefficient. It gives you everything correlation coefficient does, but it gives you a little extra information that makes it even more useful. So we have the GRE score from low to high, and we have GPA, and we have the dots on the line, the dots on our scatter plot, what this is called. I'm trying to draw about the same one, and we have an oval. And I said on that other one, you can draw approximately the line of best fit. Well, regression gives you the line of best fit. So it actually calculates that for you. And I'm going to tap some old memories here. Predicted y, the equation of a straight line, equals mx plus b, whereas m is the slope. How does this line go? Really high, really low? Does it is it flat? That would be a slope of 0. Is it almost straight up? That would be a slope of 1. Okay, so that's the slope. And the b is the y-intercept, where it goes there. And once you know how much this line moves up, where this line moves up and down and where it sticks to the y-axis, you have a fixed point on there. So predicted y equals mx plus b. And let's take this out of the abstract and say predicted, because mathematicians talk in the abstract, but they forget that we don't work in the abstract. Predicted GPA, our outcome, equals our slope times GRE score plus B. And that is our prediction. The regression gives you the y-intercept. I forgot to write this, sorry. B is the y-intercept. So the regression equation gives you the y-intercept and it gives you the slope. And then you can actually do a calculation. So let's say the slope here, I'm making numbers up now, is 0.5, and this is plus 100. We could, and my numbers aren't going to work out at all because I'm making stuff up on the way. We could put in our GRE score into this equation, multiply it by 0.5, add 100, and we'd get the predicted GPA. Now, the prediction is only as good as any prediction. Remember, this is a big oval. There's lots of error in this oval. And it is a prediction. It says that if we have a GPA of about this right here, if we have a GRE score here, we can use it to calculate this is what the GPA, and that's what the equation will give you, that exact number here. And so regression does one step beyond. It does give you the correlation coefficient, it does give you the R squared, and it also gives you the slope and y-intercept so you can predict, which can be really useful. Let me give you a real world example. What I used to do in my former life in consulting is I used to predict CEO, among other things. I was a compensation consultant, so I would predict CEO pay from a company size measure. And we would literally do the regression across a whole bunch of companies. Let's say in the insurance industry, company size is measured by assets, how much they have in the bank, more or less, and CEO pay. And we would literally predict a CEO pay value. And companies could then set new CEO pay by putting in their assets and making an estimate of the CEO pay. And you, by the way, are beyond what a lot of those CEOs could do, because they would have to use the graph. We would literally have them use a ruler on the graph to figure it out, rather than the predicted. That hat over there means predicted y equals mx plus b. So in this case, predicted CEO pay equals to m times assets plus whatever the b is. And that's regression. So it gives you a correlation coefficient, an R squared, a statistical significance. You're looking again for P less than 0.05, and it also gives you the slope and the y-intercept. Next, we're going to talk about multiple regression and path analysis, which just go deeper into this.